This podcast will continue our discussion on the histology of the ear. And let me pick up here where we left off in the last podcast. There are 6 sensory areas of the membranous labyrinth in each ear. We know that there are 3 semicircular canals. Each semicircular canal has a crista ampullaris. There are 2 macula, one in the utricle and one in the saccule. And of course the organ of Corti is within the Cochlea duct. So these are the 6 sensory areas within the membranous labyrinth. The semicircular canals detect angular acceleration, and these are 3 arch-shaped tubes in each ear. They're fluid-filled spaces. They're filled with endolymph, and they're joined to the utricle. The superior semicircular canal is in the vertical plane, and it detects anterior to posterior movement of the head. The posterior semicircular canal, also in the vertical plane, detects lateral to medial movement of the head, and the lateral semicircular canal is in the horizontal plane, and it detects lateral to medial movement of the head. As we said, the ampulla are the sensory portions of these semicircular canals, and the structure involved here is called the crista ampullaris. The crista ampullaris has columnar supporting cells, also called sustentacular cells, and it has 2 types of sensory cells called hair cells. The sustentacular cells are specialized cells. They secrete a gelatinous covering which is over the hair cells. This gelatinous covering is called the cupula, and it's shown in the diagram like this. The cupula is surrounded by endolymph, and the cupula is deflected in response to angular acceleration, and this will generate nerve impulses in the hair cells. Now the diagram here shows these sustentacular cells or supporting cells, and then 2 types of sensory cells. Type 1 hair cells are like a flask-shaped cell. They have very large afferent nerve endings that synapse around most of the cell body, and they have fewer efferent nerve endings. They have a kinocilium. It's got a 9+2 arrangement of microtubules, but it's not motile, and the type 1 hair cell has many stereocilia. These stereocilia, recall, have actin cores. The stereocilia are anchored together in the terminal web and at the tips. And then there are type 2 hair cells, which are a columnar-shaped cell. They have mostly efferent nerve endings, 1 kinocilium, and again many stereocilia. Here is a histological view. The section here is through the vestibule of the inner ear, and the section on the left is at a higher magnification of the crista ampullaris. This would be the crista ampullaris. Here would be the hair cells, and this is the cupula associated with this crista ampullaris. Here we're showing the bone, and so the bony labyrinth, the membranous labyrinth like so, is shrunk away a little bit, but it's filled with endolymph. So you can see here a crista and here a macula. And this just shows how the semicircular canal and the utricle are coming together in the vestibule. So here is the crista ampullaris, and here would be the macula in this utricle. And this diagram just puts it into perspective. You can see the utricle here and one of the semicircular canals. So we're somewhere in one of these regions. The utricle and saccule sense linear acceleration. The utricle contains a horizontal macula. The saccule contains a vertical macula. The macula contain type 1 and type 2 hair cells. Stereocilia from the hair cells are embedded in a gelatinous sheath, and interestingly, this gelatinous sheath also contains otolithic crystals. These otoliths consist of calcium carbonate and protein. The otoliths have a greater density than the endolymph. So as motion is detected, this fluid moves through these structures, and the movement deflects the otoliths. That causes the hair cells to generate nerve impulses. So what we're getting is a repeated theme here. Hair cells in the Crista ampullaris are embedded in the cupula. Hair cells in the macula are embedded in a gelatinous matrix over which lies otolithic crystals. And here's a scanning electron micrograph of these otolithic crystals in the inner ear from humans. Hair cells in each sensory region function as mechanoelectric transducers. Here we can see by scanning electron microscopy the stereocilia and the single kinocilium on a hair cell, and here you see an image by transmission electron microscopy of the kinocilium and the stereocilium. The kinocilium is a non-motile cilia, has a 9+2 arrangement of microtubules but no basal body. The stereocilia contain mechanical gated channels. The stereocilia will deflect towards the kinocilium. That will open a mechanically gated potassium channel. When that channel is open, an influx of potassium causes depolarization of the hair cell. That depolarization causes a calcium channel in the basolateral surface to open. That will generate an action potential in afferent neurons. Now the stereocilia will deflect away from the kinocilium. That will close the mechanically gated potassium channels. That will cause the hair cell to return to its resting potential. Now something that's rather interesting, it's a little bit of trivia, you don't really have to remember them, but hair cells in the vestibular system retain a kinocilium. Hair cells in the auditory system lose that kinocilium, but they retain a basal body. There are two types of hair cells that are structurally different from each other. The type 1 cell is a large flask-shaped cell. The type 2 cell is a more columnar-shaped cell. The type 1 cell has very large afferent neurons impinging on them. The type 2 hair cells have fewer afferent and more efferent neurons impinging on them. It's thought that the type 2 hair cells might actually modulate the output of the type 1 hair cells. Now, in both type 1 and type 2 hair cells, the stereocilia are linked to each other, and their bending is coordinated as ion channels open and close. Now, there are thought to be special proteins that are called prestins that are in the lateral membranes of the type 2 hair cells. These prestins may also be in the lateral membranes of the type 1 hair cells. These prestins bind chloride ions in a resting state. These chloride ions can be released when the cells depolarize. That will cause the hair cells to shorten, and as you'll appreciate, as the hair cells are shortening, they're pulling on a gelatinous mass. Now this diagram shows the stereocilia are connected to each other by various proteinaceous materials, and these channels are going to open and cause the depolarization or repolarization of the hair cells. This shows displacement of stereocilia on the vestibular hair cells, and it's showing the cells that are resting state, and as they're displaced towards the kinocilium, that will cause a stimulation and depolarization of the hair cell. As they're displaced away from the kinocilium, that will cause hyperpolarization, and the cells will return to a resting state. The cochlea is a coil of 3 tubes that winds around a bony axis. This bony axis is called the medialis. Running through this bony axis are spiral ganglion, blood vessels, and the branches of the cochlear nerve. The scala media is actually the cochlear duct. It contains endolymph, and it is continuous with the lumen of the saccule, and it contains the organ of Corti, and that's highlighted like this. And on the bottom diagram, this just shows a portion of the organ of Corti. The scala vestibula is above the cochlear duct. It contains perilymph, and it begins at the oval window. The scala tympani is below the cochlear duct. It contains perilymph, and it ends at the round window. And the scala vestibula and scala tympani are actually continuous with each other at a structure called the helicotrema. This is a histological view of a human cochlea. It shows part of the bony labyrinth like this, and the modiolus with the cochlea wrapping around the modiolus. In some animals, the cochlea wraps around the modiolus many times. In the human, it only wraps about 2 3/4 times. Here, by scanning electron microscopy, you can see the modiolus and the scala or the cochlear ducts that would wrap around the modiolus. The scala media is an endolymph-filled structure, contains the organ of Corti, and the basilar membrane is on the basal surface. The basilar membrane is suspended by the spiral lamina and the spiral ligament. The stria vascularis is on the lateral surface. The stria vascularis consists of cuboidal epithelial cells, 3 different types of cells. There's a marginal cell, which is involved in potassium transport. There's an intermediate cell, which contains pigment. We don't know what the function of the intermediate cells are. And then the basal cells overlie the spiral ligament. These may be stem cells. As we said, this epithelium is unusual. It's a vascularized epithelium, and it secretes the endolymph. And then the vestibular or Reisner's membrane is on the apical surface. There are 2 layers of simple squamous epithelium on the Reisner's membrane. Between each of these epithelial layers is a basal lamina. This is a histological view of the cochlea. So here would be the cochlear duct, the vestibular or Reisner's membrane with the scala vestibula on the top, the scala tympani on the bottom. The basilar membrane would be shown here. This would be the stria vascularis, which would secrete the endolymph, which fills this scala media. Spiral ligament is shown here, and osseous spiral lamina shown here that help to support the basilar membrane, and then spiral ganglia shown here. And here you can see the bone of this is part of the temporal bone, and it would be the hollowed out area of the bony labyrinth. So this would all be the membranous labyrinth. The organ of Corti is the sensory component of the cochlea. It's bounded above by something called the reticular lamina, and that's shown here. And the reticular lamina is actually formed by the apical boundaries of the hair cells and by phalangeal cells. The phalangeal cells are supporting cells that support the hair cells. What's shown here are the stereocilia that are embedded into a structure called the tectoral membrane. The stereocilia are, of course, components of the hair cells. There are 1 row of inner hair cells, which are type 1 hair cells, and these have predominantly an afferent nerve supply. These sensory cells respond to sound. There are 3 or 4 rows of outer hair cells. These are type 2 hair cells that have predominantly efferent nerve fibers. These type 2 hair cells may fine-tune the signals that come from the inner hair cells. As we've said, the stereocilia, both the inner and outer hair cells, are embedded in the tectoral membrane. The tectoral membrane would therefore be analogous to the cupula of the Crista ampullaris. The organ of Corti is bounded on its basal surface by the basilar membrane, and it's bounded medially and laterally by border cells and Hensen cells, and these cells are not labeled here. On the diagram, you can see the phalangeal cells, and these phalangeal cells provide support for the hair cells, and as I've said, they contribute to the structure of the reticular lamina. Notice the inner phalangeal cell almost totally surrounds an inner hair cell, where these outer phalangeal cells don't really surround the outer hair cells. The outer hair cells rest within an indentation on these outer phalangeal cells, but the outer phalangeal cells do put forward a process which, together with the hair cells, makes up this reticular lamina. Now, not labeled here are the intradental cells, which secrete the tectoral membrane. Here's the histological view with the diagram that we've just showed you. So here would be the tectoral membrane coming down. You can't really resolve in the histological section here the reticular lamina, but in the diagram you would see the reticular lamina here, and then the hair cells penetrating through the reticular lamina and are embedded into the tectorial membrane. Stria vascularis shown here, secreting the endolymph. Now, a point I would like to make: the stereocilia of these hair cells are embedded in the tectoral membrane, but the basal lateral components of these hair cells are bathed in a substance called Corti lymph, which has got a unique composition that's separate from the endolymph, which would bathe all of this area. Now here, let me go back. If you would imagine, peel away this tectoral membrane, and here you can see the apical boundaries of the hair cells, the outer hair cells here, 3 rows of them, an inner row of hair cells. Here are these phalangeal cells that are putting out a process coming around the hair cells and making part of this reticular lamina. So here in the transmission micrograph you can see these outer phalangeal cells. Here are the outer hair cells. Here is a diagrammatic view of this outer hair cell sitting in a facet, if you want, in the outer phalangeal cell for the hair cell, and here this outer phalangeal cell putting out a process coming around the hair cell and forming something called this apical cuticular plate. Here you can see this apical cuticular plate here or here. These apical cuticular plates make up part of the reticular lamina. So the apical cuticular plate of the phalangeal cells and the apical boundary of the hair cells make up this reticular lamina. And here would just be a little bit of profile off the image of the stereocilia that would be embedding into the tectorial membrane. Here would be the hair cells. Here the stereocilia of the hair cells that would be embedded into this tectorial membrane, which has been peeled away. Here, just a higher magnification, so you can see the hair cells, the inner hair cells, the outer hair cells, the tectoral membrane that would have been peeled away here. This would be part of the reticular lamina. So this would be part of the reticular lamina like this. Histological view, you can see the organ of Corti like so, a little bit higher power view, the organ of Corti, the tectorial membrane. Here would be this reticular lamina. The tectoral membrane shrunken away a little bit here. Back on this view, the stria vascularis, the organ of Corti, the basilar membrane. This is, of course, the structure that's deflected as fluid is displaced, as sound comes through. Here's Reisner's membrane. Here, a higher power view of the tectoral membrane. So, getting back to what we talked about in the first podcast, the sound waves are collected and transmitted from the external ear to the middle ear, where they're converted into mechanical vibrations by the tympanic membrane and by these ossicles. At the oval window, mechanical vibrations are going to be converted into fluid vibrations within the middle part of the ear. And these fluid vibrations are going to cause a displacement of this basilar membrane. And this is the basilar membrane that's being deflected. The basilar membrane, as we know, sits under the auditory sensory hair cells, and its displacement stimulates the hair cells, which are going to discharge a nerve impulse. Now, we talked about this very briefly at the beginning of the first podcast. This basilar membrane has an interesting structure. It's narrower and thicker near the beginning. It's thinner but wider at the end of the structure, and high-frequency sounds are detected at the beginning of the basilar membrane. Lower frequency sounds are detected at the end of the basilar membrane. And understand that basically this basilar membrane is deflecting up and down as the fluid is moving through the fluid-filled space. Innervation to the inner ear is primarily from cranial nerve 8, and the blood supply is derived from vessels associated with the external carotid artery. Venous drainage is into a common medulla vein and into a vestibular cochlea vein.